All right, folks, welcome to 1.4. This is your preview to the derivatives. So, super important topic today. Given a position function, s of t equals 100 minus 4.9 t squared, where t can only vary from 0 to 4.518. This is a position function. A position function takes in time and it spits out position at time t. This is also what type of function? A quadratic function. Quadratic functions, graphs look like upward parabolas. Put a minus sign, it becomes a downward parabola. Put a plus 100 and you're shifting it up. So what graph do you get? You get this graph. But we're going to limit the domain to 0 to 4.518. 0 to 4.518. So I'm only going to draw this portion of the graph, the part I'm actually going to use. All right, well, what are some basic things that I could calculate using a position function? Position. That's what I could calculate. So if I want to know the position at time 0, well, plug in 0 here and you get out 100. So at time 0, the position is 100. That's my vertical intercept, right? S of 4.518, the last of the numbers, should come out with the position of 0. So I plug in 4.518, 100 minus that will give me 0. That's that point right down there. These are the important points, right? All right, I can find any point I want on this graph. Let's say I decide to choose the independent value 2. I could stick it into the function. Out would come 80.4. If I stuck in 3, I'd get 55.9. If I stuck in a number like 2.01, out would come 80.204. Now look on this graph with me. You see 4 points. 0, 100, 4.5180, 2, comma s of 2, which we know is 2, comma 80.4. And you see this other arbitrary point, t, comma s of t. I mean, any point on this graph really goes by t, comma s of t. Keep that in mind. All right. Now let's look over here. One other quick statement I'd like to make about this is you should be putting these things on your graphing calculators and using 3 decimal places of accuracy. Notice this thing has 3 decimal places of accuracy, and these do too. They just happen to have zeros at the end of them. How do I put this in my graphing calculator? I go to the y equals screen and I put in the formula. Then, if I graph it in like a Zoom standard window, I'm not going to even see it. Because my vertical intercept's up at 100, and the domain I'm looking for is 0 to 4.518. So this is what I'm going to do. I'm going to hit my Windows screen. You should be doing this on your graphing calculator, by the way, right now with me. X-min should be 0, X-max should be 5, Y-min 0, Y-max 100. And then to get these values, you shouldn't be typing this in every time. You should be using the trace function. Just hit 0, enter, and it'll come out with 100. Or 4.15, it'll come out with 0, and so on and so on. All right, folks, a few more things you need to know about the position function. First, this position function takes in time t in seconds and puts out s of t position in meters. Now, I tell you that, but you could have figured it out from negative 4.9. Negative 4.9 is half of negative 9.8. And from physics, you know, negative 9.8 meters per second squared refers to the downward force of gravity. Okay, then that makes sense. Looking over here at the graph, let's try to interpret what this problem might mean in light of the downward force of gravity. As time moves forward from 0 to 4.518, position seems to change from 100 down to 0. Is this one of those falling object problems again? It sure is. In this setup, a man is standing at 100 meters above the ground and he's dropping a ball. It takes 4.518 seconds for the ball to hit the ground. What drives it down? The force of gravity. All right, last few things you need to know, and this is super important. In your world, in the world of position, velocity, acceleration, in Calc 1 and 2, only straight line motion. You can move horizontally along like an axis. Maybe they say a particle is moving along an x-axis according to an equation. Okay, in that case, that's your positive direction, that's your negative direction. And more often than not, you have an object dropped from a high location, or maybe tossed straight up, comes straight down, might even bounce. As long as it's moving along a straight line, positive direction, negative direction. That's pretty much what you get in these problems. Last thing, most important thing for what we're doing in 1.4 and into 2.1 is this idea of velocity. Velocity is the rate of change of position with respect to time. Go ahead and say it out loud. Velocity is the rate of change of position with respect to time. It's also known as the change in position over the change in time. That is what is meant by velocity. You understand velocity. Velocity is speed with direction. Every time you get in your car and you travel, maybe at time 0 you're at your house and you travel along a straight line to the grocery store, and maybe it takes you 30 minutes to get to the grocery store. And the grocery store was, say, 60 miles away. Well, it took you traveled 60 miles, that's your change in position. It took you 30 minutes, which is a half an hour. So you went 60 miles in a half an hour. So how fast were you going? 120 miles per hour, that's pretty fast. Anyway, so you get the point. Velocity is speed with direction. Now, look with me. I'm going to show you the big trick here. On this graph, can you find time? Yes. Time are these independent values, like 0 or 2 or t or what a 4.518. Can you find position? Sure, these are the dependent values like s of t or s of 2 or 100 or 0. Now, on this position function graph, can you find velocity? No? But it's there. And you know where it is? Interestingly, it is there in the slope of the graph of S. In the slope of the graph of S. And we'll explore why that is right now. All right, folks, if you want to calculate velocity with a position function, you use the difference quotient. This is a difference quotient. It is a quotient of two differences. If I want to find the average velocity on the interval from 2 to 3, I use the difference quotient with 2s of 2 and 3s of 3. Those are the 2 points I need to use for my difference quotient. And I get negative 24.5 meters per second. Well, I could also take average velocity on a smaller interval, like 2 to 2.1, using 2s of 2 and 2.1s of 2.1, and I get negative 20.090 meters per second. I can take the average velocity in an even smaller interval than that, and if I do that, I get negative 19.6 meters per second. Look over here on the graph. Notice that if I take these 2 points, 2s of 2 and 3s of 3, just like here, 2s of 2, 3s of 3, the slope of the line that goes through those 2 points is given by the difference quotient. S of 3 minus S of 2 over 3 minus 2. You've known this forever. So in other words, the slope of the secant line through the 2 points gives you the average velocity on 2 to 3, if this is a position function. All right. Back over here. What if I want to know the instantaneous velocity at time t equals 2? Like I want to know the actual velocity at time 2, right at that time. Can I do that? Sure, I can do that. This is an average velocity with 2 very separate points. But what if I look from 2 to 2.1? Well, what would that do to this point? It would slide in much closer. What about 2.01? Even closer. What if I tried to drive this point, 3s of 3, all the way to 2s of 2, like infinitely close to it. So I still had 2 points, and I could still create a secant line to get the slope of it, this difference quotient. Here's I have 2 points and a difference quotient, 2 points and a difference quotient. But what if I drove these 2 points infinitely close to each other? You know what? The slope of the secant line will become a slope of a tangent line, and I'd be getting effectively an instantaneous velocity at t equals 2. Because the distance between them will be negligible, infinitely small. All right, so this is effectively what this limit is doing right here. This is a limit of a difference quotient. 2s of 2 doesn't change. 2s of 2, 2s of 2, 2s of 2, 2s of 2, that doesn't change. But look, 3s of 3, 2.1s of 2.1, 2.01s of 2.1. We're getting this point right here closer and closer and closer to point 2s of 2. How do you make it infinitely close? What method do we have for that? Limits. So here I just go the limit as t approaches 2 of s of t minus s of 2 over t minus 2. And what does this do? This is telling you t is getting infinitely close to 2. And what is s of t going to get? Infinitely close to s of 2. If this effectively brings the 2 points together and takes their slope. And that is going to be instantaneous velocity at time t equals 2. All right, so let me run this back for you using the graph. We said that the average velocity in 2 to 3 is given by this difference quotient right here. A change in position over a change in time is velocity. All right. Let's look over here at this graph. If t equals 3, look at, this is the point 2 comma s of 2, and here would be 3 comma s of 3. And I could draw a line, that blue secant line through it, and get the rise over run, the change in position over the change in time, the velocity, the average velocity over that interval. And what would it be? It would be negative 24.5 meters per second. Or I can move a little closer to 2 and stick in 2.1. If I stick in 2.1, look, these 2 points right here yield this orange secant line. And yeah, I'll get a slope of negative 20.09 meters per second. But if I get even closer to 2, like the red point, 2.01, 2 points are really close, only 1/100th of a second apart. I'm going to get this red line here going through these 2 points, and they'll have a rise of a run, a slope of negative 19.6 meters per second, which will be the average velocity over that interval. But what if I drove t all the way to 2, so that t got infinitely close to 2? Still have 2 points, 2 s of 2 and t s of t, but they're infinitely close to each other, whatever that means. Well, then effectively I'm going to get this black line right here, which is going through this blue point and a black point that's nearly sitting on top of it, if not sitting on top of it. Okay, and this black line then will not only be a secant line going through 2 points, but it'll be a tangent line as well. And its slope is going to be negative 19.6 meters per second. And that is what v of 2 is. That is the instantaneous velocity at time 2. That corresponds to this limit. The limit as t approaches 2 of s of t over minus s of 2 over t minus 2 equals negative 19.6 meters per second. All right, folks, we want to wrap this up and wrap this up well, so we have to compare 2 limits. The limit as t approaches 2 of s of t, and the limit as t approaches 2 of this difference quotient. They're very different, okay? If I asked you what's the limit as t approaches 2 of s of t, what am I asking you? Well, it's the limit as t approaches 2 of s of t. That's s of t, right? You know how to do this. As t approaches 2, this polynomial will approach what? We plug in 2, get out 80.4 meters. So as t approaches 2, s of t approaches 80.4. You know that you get that. But that's not what we're doing when we're calculating instantaneous velocity. Instead, we're taking the limit as t approaches 2 of this difference quotient, s of t minus s of 2 over t minus 2. This gets you instantaneous velocity. This is just a limit that involves position function. This is the limit of a difference quotient involving the position function that gets you instantaneous velocity, velocity at time 2, which of course will be negative 19.6 meters per second. We say, how'd you calculate that? Well, let me show you. What does this mean? The limit as t approaches 2 of s of t minus s of 2 over t minus 2. Well, s of t is this thing right up here, so replace it with this thing. S of 2, well, we've calculated that a bunch of times, it's 80.4. Now, take 100 minus 80.4, you get 19.6. Now, you see this is a rational function, don't you? Makes sense. You started with difference quotient, you should have a rational function in there, because you had polynomial in there. And as t approaches 2, what does you do? You plug 2 in there. What do you get? 0 over 0, which is an indeterminate form, which means I don't know yet. Do more work, do algebra. And you know with these rational functions, you're hoping to try to cancel that denominator. And in fact, that's what you're going to do. Factor out negative 4.9, and you're left with t squared minus 4, which is a difference of perfect squares. That becomes t minus 2 times t plus 2. Notice t minus 2 over t minus 2 is 1. Those cancel. and you're left with the limit as t approaches 2 of negative 4.9 times t plus 2. Okay, it's down to just a simple polynomial. Plug in 2, and you get out negative 19.6 meters per second. All right, you've got to keep this straight. You've been doing limits like this all day long. As t approaches 2, what does s of t approach? But in doing the derivative, which is effectively what we just did, and getting the velocity from a position function, you're actually taking the limit of a difference quotient involving the position function. Do you see the difference? And this, from now on, is our focus, because this thing right here, this thing that gives you instantaneous velocity, is the first derivative of a function s at time 2. All right, folks, get solid with this material. It's super important. And this is it then. Here's our familiar position function, its graph. If I asked you, what is s of 2? You would tell me, if I stick 2 into my s function, out comes s of 2. S of 2 is a dependent value of s at t equals 2. A dependent value. But if I asked you what's v of 2 on the s graph, not on a v graph, but an s graph, what is v of 2? You would tell me at time 2, what is the slope of this tangent line? At time 2, what is literally the slope of the function at t equals 2? The slope of the function at t equals 2, that's v of 2. V of 2 is the slope of s at t equals 2. Do you see the difference? Given a position function, s of 2 is a dependent value, and v of 2 is the slope of the function. Both are occurring at t equals 2. Well, that wraps it up. That's 1.4, and it really got you strongly into, I think, 2.1. So, folks, I hope you really ingest this material. Watch it again if you have to. It is so foundational. That's why it took so much time to explain this one example in depth. All right, folks, you can do it.